Welcome to our exploration of moving charges and magnetism. In this chapter, we'll unravel the fascinating relationship between electricity and magnetism, focusing on how moving charges create magnetic fields and how these fields interact with matter. From fundamental laws to practical devices, we'll break down each concept step by step. Whether you're curious about the Biot-Savart law, the force on a moving charge, or the workings of a cyclotron, this journey will help you understand the core principles that govern electromagnetism. Let's begin by understanding the foundational laws that set the stage for everything that follows. Biot-Savart law is a fundamental principle that describes how moving electric charges produce magnetic fields. It states that the magnetic field at a point due to a small segment of current-carrying conductor is directly proportional to the current, the length of the segment, and the sine of the angle between the segment and the line joining the segment to the point, and inversely proportional to the square of the distance from the segment to the point. This law is essential for calculating the magnetic field produced by various current configurations and forms the basis for understanding more complex magnetic phenomena. Let's derive the expression for the magnetic field produced by a long straight current-carrying conductor. According to the Biot-Savart law, each infinitesimal segment of the conductor contributes to the total magnetic field at a point located at a perpendicular distance from the wire. By integrating these contributions along the length of the wire, we find that the magnetic field at distance r from a straight conductor carrying current I is given by B equals mu0 I/2 pi. This result is widely used in practical applications, such as power lines and electrical circuits. Now let's consider a circular loop carrying current I. To find the magnetic field at the center of the loop, we apply the Biot-Savart law to each infinitesimal segment of the loop. Since all segments are equidistant from the center, the contributions add up symmetrically. The resulting magnetic field at the center is B equals mu0 I/2r, where r is the radius of the loop. This principle is used in devices like magnetic coils and electromagnets, where a strong, uniform field at the center is desired. Ampere's-Circuital law is another cornerstone of magnetism. It states that the line integral of the magnetic field around any closed loop is equal to mu0 times the total current enclosed by the loop. Mathematically, BdL equals mu0 enclosed. This law is especially useful for calculating magnetic fields in situations with high symmetry, such as inside solenoids and toroids. It simplifies complex calculations and provides deep insight into the relationship between current and magnetic field. Let's apply Ampere's law to a solenoid, which is a long coil of wire. By choosing an appropriate Amperian loop inside the solenoid, we find that the magnetic field inside is uniform and parallel to the axis of the solenoid. The field strength is given by B equals mu0 Ni, where N is the number of turns per unit length and I is the current. This uniform field is crucial in many electromagnetic devices, including electromagnets and MRI machines. Toroid is a donut-shaped coil. Applying Ampere's law here, we consider a circular Amperian loop inside the toroid. The magnetic field inside is confined within the core and is given by B equals mu0 Ni/2 pi, where N is the total number of turns, I is the current, and r is the radius from the center. This configuration ensures that the magnetic field is strong and contained, making toroids useful in transformers and inductors. A charged particle moves through a magnetic field. It experiences a force known as the magnetic Lorentz force. The direction of this force is perpendicular to both the velocity of the particle and the magnetic field, as given by the right-hand rule. The magnitude of the force is F equals qvb sin theta, where q is the charge, v is the velocity, b is the magnetic field, and theta is the angle between v and b. This force is fundamental to the motion of particles in magnetic field. Derive the Lorentz force expression. Consider a charge q moving with velocity v in a magnetic field b. The force experienced by the charge is given by the vector cross product F equals qv times b. This means the force is always perpendicular to both the velocity and the magnetic field. This concept is crucial in understanding the behavior of charged particles in devices like mass spectrometers and cyclotrons, where precise control of particle motion is required. A charged particle enters a uniform magnetic field at an angle. It follows a circular or helical path. This is because the magnetic force acts as a centripetal force, constantly changing the direction of the particle's velocity but not its speed. The result is uniform circular motion if the velocity is perpendicular to the field, or a helix if there's a component parallel to the field. This principle is key in understanding particle accelerators and cosmic ray motion. Let's derive the radius of the circular path for a charged particle in a magnetic field. The magnetic force provides the necessary centripetal force, qvb equals mv2/r. Rearranging, we find r equals mv/qb. This formula shows that the radius depends on the mass, velocity, charge of the particle and the strength of the magnetic field. It's a fundamental result used in cyclotrons and mass spectrometers to separate particles based on their property. Cyclotron is a type of particle accelerator that uses a combination of a constant magnetic field and a rapidly varying electric field to accelerate charged particles in a spiral path. It was invented to achieve high particle energies for research and medical applications. Cyclotrons are widely used in physics laboratories and in the production of medical isotopes. Working principle of a cyclotron involves placing charged particles in a region with a perpendicular magnetic field and applying an alternating electric field between two D-shaped electrodes. As the particles accelerate, they spiral outward, gaining energy with each pass. The magnetic field keeps them on a curved path, while the electric field accelerates them at the right moments. This ingenious design allows particles to reach very high speeds efficiently. When a current-carrying conductor is placed in a magnetic field, it experiences a force. This force is given by F equals I L times B, where I is the current, L is the length vector of the conductor, and B is the magnetic field. The direction of the force is determined by the right-hand rule. This principle is the basis for electric motors and many electromagnetic devices. Current-carrying loop in a magnetic field experiences a torque that tends to align the loop with the field. The torque is given by tau equals NIAB sin theta, where N is the number of turns, I is the current, A is the area, B is the magnetic field, and theta is the angle between the field and the normal to the loop. This effect is fundamental to the operation of electric motors and galvanometers. Magnetic dipole moment is a vector quantity that represents the strength and orientation of a magnetic source, such as a current loop. It's defined as the product of the current and the area of the loop, M equals Ia. The dipole moment determines how the loop interacts with external magnetic fields and is a key concept in understanding magnetic materials and devices. Find the magnetic field on the axis of a magnetic dipole. We use the formula B equals mu slash 4 pi, 2m r3, where m is the dipole moment and r is the distance from the center. This field points along the axis of the dipole and decreases rapidly with distance. Understanding this helps explain the behavior of bar magnets and the Earth's magnetic field. Magnetic field in the equatorial plane of a dipole is given by B equals mu slash 4 pi, m r3, where m is the dipole moment and r is the distance from the center. This field is perpendicular to the axis and also decreases rapidly with distance. This concept is important for understanding the spatial distribution of magnetic fields around dipoles. Moving coil galvanometer is a sensitive instrument used to detect and measure small electric currents. It consists of a coil suspended in a magnetic field. When current flows through the coil, it experiences a torque, causing it to rotate. The angle of rotation is proportional to the current, allowing precise measurements. Galvanometers are fundamental in electrical measurements and instrumentation. Principle of a moving coil galvanometer is based on the torque experienced by current-carrying coil in a magnetic field. The coil is suspended between the poles of a magnet, and when current passes through, it rotates due to the magnetic torque. The restoring torque from a spring balances the magnetic torque, and the equilibrium position indicates the current. This principle ensures accurate and sensitive current detection. Galvanometer can be converted into an ammeter by connecting a low resistance, called a shunt, in parallel with it. This allows most of the current to bypass the galvanometer, enabling it to measure large currents without damage. The combination is calibrated so that the deflection corresponds to the total current. This conversion is essential for practical current measurements in circuits. To convert a galvanometer into a voltmeter, a high resistance is connected in series with it. This limits the current through the galvanometer, allowing it to measure potential differences across circuit elements. The scale is calibrated so that the deflection corresponds to the voltage. This method enables accurate voltage measurements in electrical circuits. Let's recap the key laws we've discussed. The Biot-Savart law explains how currents create magnetic fields, while Ampere's law provides a powerful tool for calculating fields in symmetric situations. The Lorentz force law describes the force on moving charges, and the principles of torque and dipole moment explain how currents interact with magnetic fields. Together, these laws form the backbone of electromagnetism. Electromagnets are practical applications of the principles we've learned. By running current through coils of wire, we create strong, controllable magnetic fields. Electromagnets are used in electric bells, relays, cranes for lifting heavy metal objects, and even in medical devices like MRI scanners. Their strength and versatility make them indispensable in modern technology. Electric motors rely on the force experienced by current-carrying conductors in magnetic fields. By arranging coils and magnets in specific ways, motors convert electrical energy into mechanical motion. This principle powers countless devices, from household appliances to industrial machinery and electric vehicles, making it a cornerstone of modern engineering. Particle accelerators such as cyclotrons and synchrotrons use magnetic and electric fields to accelerate charged particles to high speeds. These devices are essential for research in physics, enabling scientists to probe the fundamental structure of matter and develop new medical treatments, such as cancer therapy using particle beams. Mass spectrometers use the principles of charged particle motion in magnetic fields to separate ions based on their mass-to-charge ratio. By measuring the radius of their paths, scientists can identify and quantify different substances. This technique is widely used in chemistry, biology, and environmental science for precise analysis. Magnetic storage devices, such as hard drives and magnetic tapes, use the orientation of magnetic domains to store information. The principles of magnetism and moving charges are fundamental to how data is written, read, and retained in these devices, making them vital for digital technology. The Earth itself acts as a giant magnet, with a magnetic field generated by the movement of molten iron in its core. This field protects us from harmful solar radiation and guides compasses for navigation. Understanding the Earth's magnetic field helps in studying geophysics and space weather. Magnetic materials respond differently to external magnetic fields. Ferromagnetic materials like iron become strongly magnetized, while paramagnetic and diamagnetic materials show weaker responses. The study of these materials is crucial for designing magnets, transformers, and electronic components. Inside ferromagnetic materials, tiny regions called domains act like small magnets. When these domains align, the material becomes magnetized. Understanding domain behavior is essential for developing better magnetic storage and improving the efficiency of magnetic devices. Magnetic hysteresis describes how a material's magnetization lags behind changes in the external magnetic field. This property is important in designing transformers and memory devices as it affects energy loss and data retention. Materials with low hysteresis are preferred for efficient energy transfer. Magnetic shielding involves using materials to block or redirect magnetic fields, protecting sensitive equipment from interference. This is crucial in medical imaging, electronics, and scientific experiments where stray magnetic fields can cause errors or damage. While this chapter focuses on magnetism from moving charges, it sets the stage for electromagnetic induction, where changing magnetic fields produce electric currents. This principle underlies generators, transformers, and much of modern electrical technology, making it a natural next step in your studies. Magnetism isn't just a laboratory phenomenon, it's all around us. From the magnetic strips on credit cards to the speakers in your headphones and the motors in your appliances, the principles of moving charges and magnetism power countless aspects of daily life. Recognizing these applications helps connect theory to the real world. Working with strong magnetic fields requires safety precautions. Magnetic fields can affect electronic devices, medical implants, and even attract metal objects unexpectedly. Understanding these risks ensures safe handling in laboratories and industrial settings. Magnetic fields play a vital role in medicine, especially in imaging techniques like MRI. These machines use strong magnetic fields and radio waves to create detailed images of the body, aiding in diagnosis and treatment. Understanding the physics behind MRI helps appreciate its power and limitations. For centuries, humans have used the Earth's magnetic field for navigation. Compasses align with the magnetic field, helping travelers and explorers find their way. Even today, magnetic sensors are used in smartphones and GPS devices to enhance navigation accuracy. Magnetic fields are essential in communication technology. Microphones, speakers, and data storage devices all rely on the interaction between electricity and magnetism. Understanding these principles helps in designing better communication tools and networks. Industrial applications of magnetism include magnetic separation, lifting heavy metal objects, and controlling machinery. Magnetic sensors monitor positions and speeds, while magnetic brakes and clutches provide smooth operation in vehicles and machines. Research in magnetism continues to uncover new materials and phenomena such as superconductors and magnetic nanoparticles. These discoveries have the potential to revolutionize energy transmission, data storage, and medical treatments, making magnetism a vibrant field of study. Emerging technologies like magnetic levitation trains, advanced medical imaging, and quantum computing all rely on the principles of magnetism. As our understanding deepens, new applications will continue to shape the future of transportation, healthcare, and information technology. Let's review the key formulas from this chapter. Biot-Savart law for magnetic field calculation, Ampere's law for symmetric fields, Lorentz force for moving charges, and expressions for torque, dipole moment, and field strengths. Mastery of these formulas is essential for solving problems in electromagnetism. In tackling problems in magnetism, start by identifying the symmetry and choosing the right law, Biot-Savart or Ampere. Draw clear diagrams, keep track of vector directions, and use the right-hand rule for forces. Practice is key to mastering these concepts and applying them confidently. Conclusion: the study of moving charges and magnetism reveals the deep connections between electricity and magnetism, shaping our understanding of the physical world. From fundamental laws to transformative technologies, magnetism continues to inspire innovation and discovery. Keep exploring, and you'll find magnetism at the heart of science and technology.